How's it going? This is Mike coming back at you with another video on number theory. In the previous video, we introduced the concept of two numbers being congruent to each other modulo n, some other whole number. We talked about the definition of that, what does that mean, and we went through some basic properties of the congruences modulo n. And I also went through a couple very, very low level, very, very basic congruence problems. In this video, we're going to go through a few more. These are going to involve much larger numbers, including larger numbers raised to large powers, and we're going to see how we deal with these guys here. Now, when we do these problems, there are certain tricks that I will recommend that you perform in every kind of problem that you will see from me. But there is a certain amount of just trial and error, playing with things, seeing what can make things work for you. There is more than one way to get to the correct answer. You'll see that as we go through these problems. Whatever way you take, it should lead you to the same correct answer, but there are many paths that you can go down to get to the same answer. But first one here, what is 97 to the 90th power mod 13? So here's the first trick that I suggest you pull. If the base is larger than your n value, then take that base value mod 13 and see what that's going to be. Whatever that is going to be, you can take that number and raise it to the same power as what you're given in the problem, and that number raised to that same power is going to be congruent to the given number that we see here. This goes back to one of our properties from the previous video, where if a is congruent to b mod n, then a to any power is congruent to b raised to that same power mod n. So since 97 is congruent to 6 mod 13, 97 to the 90th power is congruent to 6 to the 90th power mod 13. And if you just think about those two numbers, 97 raised to the 90th power and 6 raised to the 90th power. Yes, 6 raised to the 90th power is still going to be a very, very large number. However, it is significantly smaller than 97 raised to the 90th power. So already we're taking our number down a lot, but unfortunately it is still very large. So we do have to do some work with this guy here. So once you've taken the modulo of your base, you'll then be working with the exponent. In this case, the 90 here. Now, there's many ways you could go from here. What I would recommend is try to find some fairly low power of your base, and choose it so that that power is a nice factor of the exponent that you currently have. So here I have 6 to the power of 90. I could consider 6 squared, or 6 cubed, or 6 to the 5th, or 6 to the 9th, 6 to the 10th, whatever. But take a smaller power of your base, in this case 6, and again, choose your power so that it's a factor of the exponent that you currently have, and figure out what 6 raised to that smaller power is modulo 13 in this particular problem. You should choose your power. You should choose your power so that it's small enough so that you can plug it into your calculator and you get some actual number, and then from there you can, without much trouble, figure out what that number will be modulo 13. So what I chose to do here was I chose to look at 6 raised to the 5th power. And 6 to the 5th power is 7,776. And that is congruent to 2 modulo 13. Now, just as a quick recap, how can you figure that out? If you do 7,776 divided by 13 and plug that into your calculator, you'll get a whole number and then some numbers after your decimal point. Well, just take the whole number part of that and multiply it by your n value. Multiply it by your 13. You'll get some whole number. Subtract that whole number from the 7,776, and that result that you get is what goes here. So 7,776, or 6 to the 5th, is congruent to 2 mod 13. Here's how I'm going to use that. And it's not a way that we would typically think of doing such a thing, but it is still valid. So 6 to the power of 90. I found 6 to the 5th power. Well, if I take 6 to the 5th and raise it to some power, I can get 6 to the power of 90. And that power that I have to raise the 6 to the 5th to is the 18th. Because recall, properties of exponents say that if you're going to take something and raise it to a power, so say we have a to the b, and that's all being raised to the power of c, that's equal to a to the b times c. So 6 to the 90 is 6 to the 5th raised to the 18th, and that, as we found, 6 to the 5th was congruent to 2 mod 13. So 6 to the 90 is then congruent to 2 to the 18th mod 13. Now, another thing about choosing your power here, why did I choose to go with this power of 5 here? Well, not only is 5 a nice factor of a 90, and not only would this exponent here be a whole number, trying 6 to the 5th and seeing what it is and finding that taking that mod 13 gives me a nice low value of 2 is a better situation that you can put yourself in, because that means it's a smaller number that you have to work with as you continue on in this problem. If I chose, say, 6 to the 10th, I could have come up with, let's say it was, let's just say that 6 to the 10th was congruent to 11 mod 13. In that case, I would have an 11 here, and I'd have a smaller power here, but I still have a base that's larger. So I'm working with a nastier number in my base, which is not as preferable. So when you're at this step here, and you're trying to figure out, okay, what nice smaller power of 6 can I work with to break this large thing down to, try to pick a power such that when you figure out what your base raised to that power is, try to pick a power so that what it is modulo your n value is something pretty small. But we see here, we have 6 to the 90 is congruent to 2 to the 18th mod 13. 2 to the 18th is a small enough number where we can plug this into our calculator and we can get the full thing for it. 2 to the 18th is 262,144. And if you divide that by 13, you will get a whole number and then some numbers after your decimal. Take 13, multiply it by that whole number, you'll get some product. Subtract that product from the 262,144, and you are left with 12. So 2 to the 18th is congruent to 12 mod 13. And congruence modulo n is transitive. So 97 to the 90th power is congruent to 12 modulo 13. And this is the general set of steps that we go through to solve these kinds of problems. First thing you would do, take the modulo of your base with whatever n value you have. Take your base modulo n, simplify that, make that smaller first, and make your overall number a lot smaller. Then with that new base that you have, take your base and figure out what a nice power, a nice low power of that base is, modulo your n value, and try to choose your nice small power such that, one, it's a factor of the exponent that you currently have, and B, your new small base raised to that small power, when taken modulo n, gives you a nice low value. And then from there, you may have to repeat that step once more. You may have to take another smaller power of it, and again, choose it nicely so that it's a factor, and what you find modulo your new base raised to that smaller power is nice and low. But keep doing that until eventually you can get this down to a number that you can plug into your calculator, you see the whole thing, and then divide by your n value and find what your remainder is. So here's another example, larger base and larger exponent. What is 173 raised to the 1,000th power modulo 10? Another way to say this is, what is the digit in the ones place of 173 raised to the 1,000th power? When you take a number mod 10, you are getting rid of all the numbers in the tens place and to the left. You're only left with what's in the ones place. But once again, we're going to start by taking our base modulo 10. 173 mod 10 is 3. So 173 to the 1,000th will be congruent to 3 to the 1,000th mod 10. So again, we've already made our number significantly smaller. There's just, we just still have a large number that we have to work with. And now I'm going to take 3 to a smaller power. And let's try to choose a power so that when we raise 3 to that power and we take that number mod 10, we get something nice and low. The two best cases you could come up with are 0 and 1. Because if your number is congruent to 0, then you have 0 raised to any power, which is 0. Or if it's congruent to 1, you have 1 raised to any power, which is 1. Well, I look at this. I know that 3 to the 4th is 81. If I take 81 mod 10, I get 1. I had 3 to the 4th. 4 is a nice factor of 1,000. So that's the guy that I'm going to use here. 3 to the 4th is 81, as we just said. That's congruent to 1 mod 10. So 3 to the 1,000th is the same thing as 3 to the 4th raised to the 250th power. We make that substitution here. The 3 to the 4th is congruent to 1 by what we just stated. So 3 to the 1,000th is actually congruent to 1 to the 250th power. And as we just said, 1 raised to any power is 1. So, therefore, 173 to the 1,000th power is congruent to 1 modulo 10. We know that the digit in the ones place of this massively, massively, massively large number is going to be a 1. Next two examples, slightly more involved. We're working with sums of things here. Just one extra little side chunk of work that we have to do, but we're still going to do the same process of take your bases, take them modulo your n value, then work on your powers that you have, and simplify those things out, reduce those things. So here I have 77 to the 11th plus 11 to the 77th. And what is this number? Mod 9. So we're going to work with each term in the sum separately, and then we're just going to add the two results that we get. Recall from our previous video, we said that if A is congruent to B mod n and C is congruent to D mod n, then A plus B is congruent to C plus D. A plus C is congruent to B plus D mod n. So 77 is congruent to 5 mod 9. So 77 to the 11th is congruent to 5 to the 11th mod 9. And 5 to the 11th you can actually plug into your calculator and you will get the whole number out. You will get 48,828,125. Divide this number by 9, you'll get a whole number and some decimal points after. Take that whole number portion, multiply it by 9, you get some product, subtract that product from this number right here, and when you do that, what you have left over is 2. So 77 to the 11th is congruent in the end to 2 mod 9. So this was the first term in our sum. Now we work with the second term. 11 is congruent to 2 mod 9, pretty basic. So we have 11 to the 77th is congruent to 2 to the 77th mod 9. I want to now find a nice low power for 2, such that this power is a factor of 77, and hopefully taking 2 and raising it to that power, and then taking that number mod 9 gives me a pretty small quantity. So I chose to work with 2 to the 7th. That is 128. And when you take that mod 9, you get 2. So it's maybe not one of the two ideal cases of it being 0 or 1, but it's the next best thing, which is 2. So 2 to the 77th is equal to 2 to the 7th raised to the 11th. And we said that the 2 to the 7th was congruent to 2. So 2 to the 77th is congruent to 2 to the 11th, mod 9. 2 to the 11th you can plug into your calculator, and you get 2048. Take that mod 9, and you get 5. So I found that 77 to the 11th was congruent to this mod 9, and 11 to the 77th was congruent to that mod 9. So we take the sum of those. 77 to the 11th plus 11 to the 77th is congruent to 2 plus 5, or 7 mod 9. Again, yes, we had 2 separate chunks of work to do, but we did the same set of steps. We reduced our base, then we found a nice smaller power that's a factor of the power that was given, and hopefully gives us a nice remainder when taken mod n. Show that, and this is going to be our last problem, show that 7 divides 92 to the 133 plus 133 to the power 92 minus 1. Now what this is saying, actually, if I call this thing, say I call this number alpha, what this question is actually asking us to do is show that alpha is congruent to 0 mod 7. That's what the question is actually asking us to find in the context of linear congruences. Now, what we're actually going to do is we're just going to look at the 92 to the 133 plus the 133 to the 92. And what we're going to do is we're going to show that that's congruent to 1 mod 7, and then the desired result will follow, because if I show that that is congruent to 1, I can subtract 1 from both sides. So I have 92 to the 133 plus 133 to the 92 minus 1 is congruent to 1 minus 1, or 0 mod 7, which we just saw from our previous slide. That's what this is actually wanting us to show. So, again, work with each term in the sum separately, and we'll see, and we'll try to come to the result that we want to get to. So I looked at the second term first here. So I'm trying to reduce the base. Well, 133 is congruent to 0 mod 7. 7 nicely goes into 133. So 133 to the power 92 is congruent to 0 raised to the power of 92. 0 raised to any power is 0. So 133 to the 92 is just congruent to 0 mod 7. That's good. That's nice and simple. Working with the other term now, the 92 to the 133. 92 is congruent to 1 mod 7, the other ideal case that we could have. So 92 to the power 133 is congruent to 1 to the power 133. 1 raised to any power is 1, so 92 to the power of 133 is congruent to 1 mod 7. Therefore, adding these results, 92 to the 133 plus 133 to the 92 is congruent to 1 plus 0, or 1 mod 7, and then the desired result follows when we subtract 1 from both sides. So this was a bit of a friendlier sample problem, but again, it shows you the process that we go through. There's those couple main actions that we do when we solve these kinds of problems. First, we reduce the base. Then, after we have reduced the base, we then pick a nice small power of our new base, such that this small power is a factor of the exponent that we have, and the base raised to this small power is ideally a nice low number. 0 and 1 are the two best cases. But sometimes it's really hard to come up with a nice low power that will that will touch on both of those. Sometimes you can only come up with a nice small power that is a factor, but if you take your base raised to that small power, you get kind of a larger value, like maybe 6 or 7 or 8, or even larger than that. So sometimes things aren't as ideal as we want, but nonetheless, you're still reducing your number. You're still making it smaller with every time you go through that step. So those were some sample problems for this video. Some more examples where we find the congruence of a number modulo n. This time, obviously, we worked with significantly larger numbers. In the next video, we are going to talk about binary representation of integers and decimal representation as well. And we're going to talk about a neat little test for divisibility by 11, which maybe you have heard of before, but maybe you haven't. If you have any questions or comments, please be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.